My paper is titled Real-Time Anomaly Detection for Multivariate Data Stream, and I'm currently a meta author. So I work at Microsoft. I'm an author of a textbook on distributed system, which is currently on the process. And yeah, Uh, and here's the link to my blog. I have this blog, and the paper link is here. You could go through it and then see this blog on these items. So anomalization is the task of classifying patterns that depict abnormal behavior. So it's suited for unbalanced data sets where you have um, rare rare abnormal events and majority normal events. So there are different categorizations like the point anomaly, contextual anomaly, and collective anomaly. So the point anomaly is like an anomaly that happens once in a time. Let's say your post on Twitter gets popular suddenly. So that's an anomaly. But then that's the point anomaly. For the contextual anomaly, let's say your post was popular yesterday, and then today it spiked, but not like what it was yesterday. So if you are doing some kind of neighborhood kind of analysis based on the surprise you had yesterday and today, this current value is no longer an anomaly compared to what you already know. You're already used to what you had yesterday. So that's like based on the context of your data. Then at the collective anomaly is like an anomaly, like you gather a series of readings from a machine, but some items are like correlated. Let's say some parts of your attributes are actually with abnormal in that simpler dimension. But in the overall dimension, it may still be normal. So you only count it anomaly as a group while viewing all the data. So not just on one part of the data. So there are multiple settings where you could use this. It will be the static or the batch method, which is like you have enough memory to save things there and do your operation. So you load everything in memory and do your operations. So the online one is just like you do everything as you did at crumbs. So then the static and online one could be like maybe at the start of your process, you may use the static method to initialize your attributes. And then when you get more data, you update in kind of Bayesian style. So yeah. Then another method can work in a number of modes, like diagnosis mode. That's like or then accommodation mode. The diagnosis mode involves removing anomaly from your data samples. But this that may skew your distribution. That may end up even skewing it. Even what you're trying to avoid, you may end up having it. So but this is only reasonable when you know there's a distribution of what the normal data would look like, and then you could use that to do that. And the recommendation one is like incrementally updating your data as it's more in line with like kind of a Bayesian formulation, and you can do that stuff. But there's a problem when you do the diagnosis method. You will have issues with contextual anomaly, like yeah, because if you delete that one, you've skewed your data already. So you will have multiple layer of skewing of your data. So you may suffer the second layering effect. Yeah. And then the data streams, there's this time and space constraint. So what is the data stream? This is data coming up like as they come. You process it as they come. So there's some challenges you could have like because you have to process things quickly, um, and then you should have a way of forgetting the past. So, like in most of our methods that we did discussing here, there is exponential moving averages where you actually put a kind of a weight on the past. So, which means if you weigh the past less, it means you want to forget the past and emphasize the present. So, those have implications in how your overall distribution works at the end. So yeah, that means some changes in your distribution. So also the aggregation you choose for your analysis. The based on the time aggregation. Let's say you have a 5 seconds aggregation of your data. You can't go below that resolution in making predictions. So what are the core contributions of my work? So my work was based on this probability exponential moving average paper by Kevin Carter and William Strelin. So they developed this method for univariate data. Then I extended it to support multivariate data stream because of this the way it works on these shifts and as shown in different sections of our paper. So you could also see like the online covariance matrix was based on a method that's like optimal. So based on just only one data, you can update everything without computing the entire stuff. So and then I extended the method. So that method was based on a paper released at GECO by Christian Idru. But what I did was for the online inverse formulation, I used Sherman Morrison formula to provide the inverse of the covariance matrix for my method. So this is just exactly what I was describing. So this is like side by side comparisons. So this is both content. So this is like calculate the invariance matrix, make a running average, updates in a kind of where your posteriors, the next posterior will become your previous priors. So and you could see me following that process all through. And then setting the threshold is very important. So we discuss that in details. So let's say this for this example, this mean 80 and this one, if we're operating within this scale, two times standard deviation. If you choose this as your threshold, so you are saying between 50 and 20 is your anomaly, and between 110 and 140 is your anomaly. So the value you choose for your threshold is very significant in which part of this curve you're choosing. You could also specify which part, if you to choose only this part as an anomaly. So those decisions will be based on your application. So if you see these are the results. So the result I was trying to consider what are the impacts of going static versus going online. So what are the losses you have? So of course the most accurate ones will be doing everything static, but your data may not fit in memory and many other constraints. So in that case, you want to do some things online. So this experiment is just to see how much losses are we getting by doing that. So read the paper for more details. Then there are some limitations of this work. For instance, for this work to work properly, you need feature selection of the attributes that captures the dynamic of your system. So and there are some limitations of our work, such as strong assumption on Gaussian distribution and inability to handle non-stationary distribution in data. So these are some references I would like you to look that my works were based on. Thank you so much for listening and enjoy the rest of your workshop.